So that's our goal. So today we're going to talk about the LP boundedness of H, and also something I'm going to call M, but the book calls it star. So the second thing we're going to talk about today is the boundedness of the Hardy-Littlewood maximal function. And I think Stein just leaves off the names and just calls it the maximal function. This is something that you start off with a function and you take its absolute value, and then you take the supremum of all averages of that function around each point. Okay. You take supremum of averages of that function on balls centered at that point, and that new function that gives you the supremum of those averages is called the maximal function. So it dominates the old function. And it turns out that the maximal function, the control of the maximal function turns out to be key in controlling singular integral operators, not just the Hilbert transform, but the generalized singular integral operators that we see later. In fact, you could sort of think of the singular integral operators, maximal functions, and a third thing called square functions, as sort of like the triumvirate of harmonic analysis. And in some sense, you think of them as almost the same thing, or very like embodying certain aspects of they're all thank you. So this is our representative from singular integrals. And this is our representative from maximal functions. Stein in this book is not really emphasizing the third guy, so-called square functions, but there's something else called square functions, which is also pretty important. Okay, so the theorem that we're going for is this one, that H, the Hilbert transform, is bounded on L2 intersect LP. LP between L and infinity. And then once you have it, because it's only, for us right now, it's only defined for L2, right? So first you show that it's bounded on LP, the functions that are, it's bounded with respect to the LP bound for the functions that are in L2, and then you extend that to, by density, you extend it to all of LP. Okay, so I'm going to just write it's bounded on LP, although so it will suffice to show it for L2 intersect LP. Okay. Okay, so let's first recall the Cauchy integral. If you have some function in L2, we define this thing, the Cauchy integral, FMC, it's 1 over 2 pi I, the integral of ft over t minus c dt, and then constant infinity. And we're going to need a couple of facts that I'm not going to prove, but I'm going to state them. First, that if f is an infinitely differentiable and compactly supported function, then its Cauchy integral extends to a bounded continuous function on the upper half plane. Okay, so this is initially defined for z where y is bigger than 0, and we're going to extend it to the closed upper half plane. So, and the second thing is that it has a certain decay that f of z z behaves like this, again in the upper half plane. So I'm just going to state these as facts. They can be seen just by calculation. I've done the calculation. It's not too exciting. If you want to see it, I can show it later. Okay. So two facts about the Cauchy integral. Okay. Then relating the Cauchy integral and the Hilbert transform. Recall that for z in the upper half plane, we have this point, f of z equal 1/2 f convolved with p of y x plus I f convolved with q of y, q sub y x. Okay. We had this formula from earlier, right, that f of z could be realized as the convolution of f with Poisson kernel plus I times f convolved with the conjugate Poisson kernel. Okay. So so from that, right, using the using the continuous extension. So this formula is true in the upper half plane, right? And using the above continuous extension, we get that if we're looking at f of x, or 2f of x, that's what we get when we take the limit as y goes to 0 of f convolved with Poisson kernel plus I f convolved with the conjugate Poisson kernel. Of course, by continuity. You just letting y go to 0. Okay. You get this thing. Right? And what's that? What is that? Or what do you think that is? And this is actually. So remember what did this turn into? Do you remember?
Hilbert?
The Hilbert transform. Right. This actually in the L2 sense converged to the Hilbert transform. But in fact, for if you go back and look how we did it, it's actually a pointwise. This actually works pointwise if your function is a Schwartz class function. Okay. So this thing actually converges pointwise to I over transform f of x. Okay. And then this other one. I don't know if you know what happens to this one. F convolved with the Poisson kernel as y goes to 0. Do you know? Does anyone know what happens to this one except for Chen?
That's a homework.
What does it say in the homework?
Prove this thing.
Prove that this goes to what? This thing actually converges to the function itself. Okay, this actually recovers the function itself. And so I think in the homework you're asked to prove this is true for LP functions, right? If f is an LP function, then this converges to f in the LP sense. But in fact, if f is sufficiently smooth, if f is, for example, in Schwartz class, And any function that's infinitely smooth and compactly supported is in the Schwartz class. Then in fact this will recover your function pointwise. Okay. And this is an example of what's called an approximate identity. So let me. I think some of you haven't seen this before, so let me review let me review or introduce to you what goes on there. So just one comment about this statement in the book. This statement here that so 2 elements equals the limit of y as y goes to 0. So this first statement here is just the continuity, right? Saying, well, we extended f to a continuous function. This is the continuity statement. Okay. This formula, you recall we showed it for, this is actually true pointwise for f in the Schwartz class. Okay, remember we proved this statement using Fabini's theorem, first on the Schwartz class functions, and then we extended it to L2. Right? So this is true pointwise. This actually is true pointwise for the Schwartz class function. And then these statements are true pointwise as well. So this is actually a pointwise true statement. Okay. So, but let me sort of go back. Let me talk a little bit about this thing here. So there's something called that we call a good kernel, and that Stein calls a good kernel. And that is you have some function k of x. You have some function k of x, and you have k delta of x, which is 1 over delta k x over delta. Okay, so it's the dilation. It's the dilation of it's the delta dilation of k. So you widen the base, you scale the base to size delta, right? And you divide by delta as well. So as you notice that that the L1 norms are the same. But that the integral is the same. So you have some function on R. If it satisfies 3 properties, so if 1, the integral is 1, 2, the integral, the L1 norm is bounded, and 3, for any eta bigger than 0, if we look at the integral of the absolute value away from the origin, then that goes to 0 as delta goes to 0. If these three things happen, then we call this family. We call this a good kernel. Yeah, Brian.
Is M a uniform bound
Yes.
in delta? Oh.
Yes. So we call this family a good kernel. And the point of having a good kernel is, well, the way you want to think about this is that these good kernels are something that get close to, or an approximate identity, also called an approximate identity. So the way you want to think about this roughly is that as delta goes to 0, k delta basically becomes the direct delta function. Okay, so we don't, for us, we don't convolve with the Dirac delta function, but it would be great to convolve with the Dirac delta function, because if we did, we would just get back our function, right? Convolving with the Dirac delta, in some sense, should recover your function. So this is sort of like a replacement for it. It's not the identity, but it's an approximate identity, right? You've got this thing, right? It has a certain mass to it, and as delta goes to 0, the support of it gets squashed in towards the origin, right? You see that for any eta, right? For any eta, if you look at the material of the kernel, well, that stuff goes to 0. Right? For any eta, as delta goes to 0, the bulk of the kernel is going to lie inside here. Right? It will start squeezing in. So basically, you want to think of this as you have some sort of bump, right? You have some sort of bump of mass 1, right? And then as delta goes to 0, that bump starts getting squeezed in, and the mass starts getting concentrated at the origin. Okay, so in some sort of limit, it approaches the Dirac delta function. Okay, and as you might expect, this thing, you can probably guess the fact that I'm going to state. So lemma, or sort of proposition, if f is Schwarzschild function, then the limit of the convolutions is the function itself, right, as delta goes to 0. So you recover your function. Okay. And this, if you think about it, the Poisson kernel. Okay, so maybe I'll prove this in a second. But if you think about the Poisson kernel, right? What's the Poisson kernel? P y x is this 1 over pi of y over x squared plus 1. Right? This is the Poisson kernel. Right? You think about P1, right? 1 over x squared plus 1. These PYs are really P1 dilated to the y scale. Right? All these guys are dilations of 1 over x squared plus 1. Right? So you have this right? You have this bump. Right? You have this bump, and then it's of mass 1. Right? If you integrate this thing, you get 1. So you have the 1 over pi. Right? You have this mass of 1, and then as y goes to 0, right? You're squashing in the support of the function. You're squashing in the material of the function towards the origin. Okay. And so the Poisson kernel is a good kernel, and for Schwarzschild functions, you actually do recover the thing pointwise. Okay. So let me sketch out why this happens, because it involves a pretty common trick. I guess I already showed you this trick before, but there's no harm to show it to you again. Actually, it's not the same trick anymore. So I'm showing you a similar trick. So in fact, this convergence occurs uniformly. Here's the proof. So first observe that f being in short class is uniformly continuous on a real line. And the reason is that because given any epsilon, we can choose some negative r outside of which the function is smaller than, say, epsilon before. Right? Because the function is decaying, faster than any polynomial, right? Faster than one over any polynomial, right? So we know that we can chop it off and it'll be tiny outside there, right? So the continuity outside there, we don't have to worry. The function is small. It's so small we have control over its oscillation up there. And then right here on negative r, it's continuous, right? So it's uniformly continuous on this side, right? So we have uniform continuity on this thing, and then we have uniform continuity on the rest of it because of just the size. So we have uniform continuity on a whole line. So because we can choose this outside of blah, and f is uniformly continuous on this complex. Okay, so here's the trick. Here's the main trick. So you say, well, okay, let's consider f involved with the kernel minus f. Let's consider the difference between this thing and f. That is right. That is going to be k delta t f of x minus t dz minus f of x. William or Eric, do you remember what happens at this point? What's the trick? So you use the fact that the integral of this thing is 1. Okay, and that allows you to slide the f of x in. So just a small trick, but it's right. Okay. Okay. So wait, device. Okay. So and then you break this integral up into two parts. This part away from the origin and the part near the origin. And you want to show that these things can be made small, independent of x. Okay. So you sort of know what's going to happen, right? What are we going to do here?
I have a question.
Yeah. One.
But you said that the good kernel is 1, so we can do the trick. But it's not 1. The integral of it is 1.
Yeah, the integral is 1. Right, so you multiply this thing by 1. Right, you multiply this thing by 1, and then you combine them together. Right, so this, you get here, you get here, this. Right, you take your f of x and you replace it with this thing. So you've got this minus this.
But this inside the integral, so I have like double integral now.
No. You have one integral minus another integral. Right? So you have one integral minus another integral. Right? So it's going to be this. That's the difference. Right? Okay. So what's going to happen at this point? How do we control the sizes of these guys? Right, we have go ahead, Brian. You have anything to say?
Well, we can either use the good kernel property number 3, or we can use that it's Schwartz class. So.
Right. Well, we really need to. What do you think? Well, we have to use that. Well, we have to use that the function is bounded, right? And property number 3. Right? The property number 3 plus boundedness of the function, right? And then here we use uniform continuity of f. Here we use uniform continuity, right? So we can make these things as small as we like, independent of x. So use property 3 and boundedness. And here we use that f is uniformly continuous. Right. And that the integral of k is 1. The uniform continuity will allow us to make this as small as we want. We can pull that out, we get the integral. This is controlled by the integral. No, that the integral of k is bounded by n. Okay. Question, Mom? Yes. Okay. So this is good, right? So this is why we have that formula. So this the Poisson kernel being a good kernel. Gives you pointwise the pointwise convergence you want. So we get that that this thing actually does pointwise recover your function. As pointwise recovery function, here we get I times the Hilbert transform. So that's pretty cool, I think. Right? You know, what does this say about the Hilbert transform? right? It says that if you have some, smooth function, compactly supported smooth function, you take the Hilbert transform of it, right? Then this is the Hilbert transform is the imaginary part of the boundary value of an analytic function, right? So you're basically finding out what function you need to add on to your function to get a function that extends to an analytic one on the upper half plane. So that's one way of thinking. The Hilbert transform, although I should say when I learned it, I learned it entirely in the real sense. It's actually tightly related to complex analysis. Okay. Yes, this one.
So, what is the relationship between the good kernel and the Poisson kernel?
The Poisson kernel is a good kernel.
It's the same.
No, it's not the same thing. So good kernel is just a general term. So this thing, approximation of the identity, is any kernel, any kernel who satisfies those three properties. Okay. Turns out that the Poisson kernel is one of them. And so you can use it to recover pointwise your function, and as you'll see in your homework, you can use it also to say things about the LP convergence. Okay. Okay. So now let's go for the boundedness of H. So I don't know if you all are if you all would like to go faster, but this is all really important stuff. So I think it's worth not rushing through it. Like I said, all of this stuff is even now really important, really hot, I would say. So just to give you sort of like a foreshadowing. Did any of you read about the maximal function?
Covered.
Oh, you've seen it before?
Yeah.
Okay. What have you seen? What did you know about it? What do you know about it?
Some properties like the weak and
The weak quality.
Oh, okay. So you already got the weak inequality. Did you use the Vitali via the Vitali coding on that? You got the weak inequality. And what are we going to talk about? Okay, well that's good. Have you all seen that? You haven't seen it. Okay, so I do have something. Anyway, it's good to see you.
That was actually it covers it in the previous book.
Okay. So there's this thing called the Hardy-Littlewood maximal function. There's this thing. Anyway, it's like the nemesis of. Anyway, it's like my personal nemesis, the Hardy-Littlewood maximal function. Well, actually, I have nothing against it. I have something against its elder brother, the strong maximal function. Okay, so there's this thing, the Hardy-Littlewood maximal function, and what we're going to see later is that the maximal function is actually bounded, and we'll do this by interpolation between a weak result and the L-infinity result. Okay. One question that comes out of this is what weights with respect to what weights W is M bounded on LP W. So you change your measure, and you change your measure by adding in some sort of density, and you ask the question, what weights do this? it turns out that that they belong to a certain class. So M will be bounded on LP if normally W belongs to a certain class called AP. A certain class called AP. Okay, and this is actually and it turns out that the singular integral operators actually behave well on these on exactly the same spaces. Okay, so these are the right spaces on which to consider the behavior of singular integrals as well. In fact, for the last up until maybe 2 years ago, there was a lot of work being done about the following question: how does the bound of a singular integral operator depend on something called the AP number, of weight. Okay, so each weight to each weight is associated with something called AP number. I don't think we'll talk about it, but this is called the A2 question, because it was shown that if you could get it for A2, you could get it for all AP, for all P. And it's only a couple of years ago that this question was resolved by Tuomas Hilbert of Finland. So I mean, this is what I need to say is that this is actually pretty recent stuff. With a lot of very very powerful minds working on it. And it's only so Tuomas Hilbert was able to get it, sort of building on the work of a lot of other people. He definitely don't want to say that he got it all by himself. People have been hitting around, getting closer and closer and closer, and finally Tuomas was able to put it all together and with his own ideas, get it, and he became super famous immediately. Yeah, there's an article about him. There's like an interview of him on the internet. It's in Finnish, and I tried to translate it using a Google translator. And it talks, if the translator is correct, it talks about how mathematicians are like drug addicts, constantly depressed and looking for a light at the end of the tunnel, but just in a constant state of depression. That's how he describes mathematics. Okay. Okay. So, right. So, proof of the boundedness of H. Okay. So, first thing we're going to get is boundedness. So first we'll assume that F is compactly supported and smooth and real value. Boundedness. First we'll get boundedness for P being an even number. So L natural number. So P is some even number. Okay. And so I don't know if did anyone read this? Does anyone have a sense of the proof? Anyone have a sense of how the proof of this goes? So like the strategy of the entire proof. So sketching out the entire proof, what happens is that one uses complex analysis to get the bounds for even P. Okay, so you get it for P equals 2, P equals 4, 6, 8, etc., etc. Okay. And then you use Reese interpolation to get the numbers between these guys. So that gives you any p bigger than 2. That gives you p bigger than 2. And then you use a trick, a duality trick to get, you're sort of stuck. You don't have, you can't get p between 1 and 2, but there's a duality trick that you use to get the results for the opposite side. So here, this is by complex analysis. This second part is by Reese interpolation. And the third part, one gets by duality. That gives you p between 1 and 2. So you get between 2 and infinity, and then you use the conjugates. You get the conjugates of that using a trick of duality. Okay. So the first part is the following claim that if you integrate f to the k from negative infinity to positive infinity, then you get 0 for all integers bigger than or equal to 2. So this is actually relies on Cauchy's theorem from complex analysis, which says that if you have f a holomorphic function and you integrate it, if you integrate it around some, if you take the integral over a closed loop in a simply connected domain, then the integral is 0. So what we're going to do here is we would like to get the integral from negative infinity to positive infinity. So what we do is we integrate over a big square. I'm sorry, a big rectangle. So you have these points, negative r plus I epsilon. You go to r negative r plus r. So you integrate, you take the integral of, so integrating f to k over this path gives 0. Integrating f over this path gives 0, and then you take the limit as r goes to infinity and as epsilon goes to 0. Okay, and recall that we have this decay condition. Okay. We have this decay condition on f in the upper half plane, right? And so that tells you that as r goes to infinity, then the integral, the integrals over these upper edges goes to 0. Right? So they don't contribute anything. So what does that tell you? That tells you that the integral over the bottom guy is 0, right? That is to say that this, in the limit, this thing is 0. So this implies that this is 0. Right. Yeah, hold on.
Can we do our contour as a circle?
Yeah, that will work as well.
Not circle, half circle.
Yes, that's fair. So, yeah, we could do something like that. We could do something like that. That will certainly work. That won't make any difference. Okay, so, so that's the proof of the claim. And the claim then implies that, well, of course, the claim is equivalent to saying that f of x plus I h of x to the k, the integral of that is 0. So, for example, if k equals 4, what you get is that, what one gets is that taking the real part, one gets that the integral of after 4 minus 6 s squared h squared plus the transform equals 0. Right? Which implies that the Hilbert transform is strictly less than, or less than equal to, excuse me, less than equal to s squared hf. Right? Because you move these guys to the other side, it's equal, and this is f to the 4th, right? Which is positive. Right? F is a real value function, f to the 4th is positive, so it's only going to get bigger when you get rid of this thing. The right side only gets bigger when you, right? It's equal when you have this, and when you throw it out of the way, it just gets bigger. And that's why we needed to use real value functions. Also, we need that f is real to get this part right here. And then by Cauchy-Schwarz, you say, okay, well, that's smaller than 6 4 to the half. That's smaller than the L2, the product of the L2 norms of those guys. Bringing this to the other, bringing this back over to the other side, and dividing both sides by that gives you the bounds for L4. So that gives you that. The L4 bound of H is 6. No, it's really 6. Any questions? Everyone seems kind of quiet. you're throwing away the positive numbers, so it only gets bigger. And then you do Cauchy-Schwarz on this, right? You know that this is going to be controlled by the product of the L2 norms of this and this, right? The L2 norm of f squared and the L2 norm of hs squared. Right? And then you divide both sides by this, right? This is right now to the first power, right? So you get to the half power here, right? So you get hf for the half power is less than 6 f for the half power. Taking the square roots of both sides gives us the L4 code. Okay. So let me the Rees interpolation. So this sort of argument basically gives you the results for. So we've only done it for L4, but you can do it for any even number basically in this way. Let me skip to the last part, the duality part, because I think that might be a little bit unfamiliar to those who haven't seen much Fourier transform. So you get the boundedness for LP, P, 2, 4, 6, 8, blah blah blah. Then you use Rees interpolation to get it for the one in between those numbers, so P greater than 2. The last part is the duality for P less than 2. Okay. And what you need is the following. For F and G, we make this observation. We see that the Hilbert transform integrate against the complex conjugate of G is the same thing as F against the complex conjugate of the Hilbert transform of G. Okay. So we can pass the Hilbert transform over to the other guy at the cost of the minus sign. Okay. And this is just a consequence of Plancherel. So, that if you're taking the conjugate of one function, if you're taking the complex inner product of one function against the other function, then for L2 functions, you can putting hats on them preserves you can put hats on them. Okay, so where this complex inner product is the function against the complex integrated against the complex conjugate of the second function. Okay, so so that is, you see, okay, well, what we're doing here, this thing on the left-hand side is the inner product of, is the complex inner product of the Hilbert transform against G, and then you say, okay, we can put hats on the both. Right? We can put hats on the both. And then let's write it out what this thing is. This thing is, well, the Hilbert transforms complex, I'm sorry, the Fourier transform of the Hilbert transform is the sine, right, over I times the Fourier transform, right? And then this thing here we have G's Fourier transform complex conjugate, right? And then you just pass it over. And you say, okay, well, let's instead put this guy over there. Right? So you get integral where you transform Hilbert transform you'd like to have a bar here, but in order to do that, you need a negative sign, right? Because you're taking the complex conjugate of that, so you just get a negative sign of that. Right? That's a pure imaginary number, right? And so that gives you negative f hat against hg, right? Against the Hilbert transform. Against the Hilbert transform of against the Hilbert transform of G, right? And then you take the hats off. And you get the right hand side. So typical sort of argument. And then here we do the duality trick to get the balance with Hilbert transform on p between 1 and 2, like this. So you say, okay, now we estimate the Hilbert transform. So for p less than 2, now, we estimate the Hilbert transform of p using lemma 4.2 again. Okay, let's take the integral the supremum. Remember, we said that if we take g simple and g p prime norm less than or equal to 1, then we can estimate the LP norm by taking the sup of the inner products of these guys. Okay. So, well, using the trick we just, using the equality we just put up, well, we can shift the Hilbert transform over to the other guy. Right? So G is simple. And P prime norm is less than or equal to 1. Right? But then, we know that that's controlled by, we can control this thing. Sorry, I should have. We know that that thing is controlled by using Hilbert's inequality. Right? So this thing is controlled by f p hg p prime. Right? Which is good because we know that h is bounded on p prime. Right? P prime is bigger than 2. Right? If p is less than 2, then p prime is bigger than 2. And we have the Hilbert transform bounded on p bigger than 2 already. Right? So so we have that this thing is bounded by bound the LP norm of h, g prime norm, that's less than or equal to 1. Right? And so we get that right, so we get that we get that the LP norm of h is controlled by the LP prime norm of h. And then you extend by the way. So this is this trick is a useful one, and it's used in other places as well. So duality. Okay. So we did not get to the maximal function as I hoped, but I guess we'll do it next time. We'll start off with the Italian covering lemma and weak type boundedness, and then. So did you get the LP boundedness of the maximal function? No, you just did the weak type. Okay, so you didn't. Okay.